All right, here we are, lesson 20.5 and 20.6 today. We're going to look at both of these lessons. The first one, we have a couple theorems, and then the second one, we have just some more information about those theorems, and we'll look at some examples of how to apply all the different theorems that we have today. Okay, so as you can see here, we have another theorem 1 and theorem 2. So we are never going to use the theorem numbers. So we're always just explaining what the theorem states. And don't tell me theorem 1 or theorem 2 because it depends on the section that you're talking about. All right, so to find the convergence or divergence of a series, we are going to learn what we call the comparison test. And the comparison test is going to allow us to take a series that we already know is either convergent or divergent and compare it to the given series that we're trying to figure out. And these two theorems give us a method for doing that. So theorem number 1 states that if each term of a given series of, let's see here, non-negative terms from some term on. So maybe it might not work for the first couple terms, but it needs to work from some term on, is less than or equal to the corresponding terms of a second series of non-negative terms for which we know is convergent. All right, so here we're looking at is a known convergent, and we're saying it needs to be less than or equal to. Then we can also say that the given series is also convergent. So kind of what that means with the series that we're looking at, since we're talking about the term, so it says from some term on, we're going to be comparing the u sub n values. So that would mean that u sub n would be less than or equal to some u sub n star, I'll call it. So the given series is u sub n is less than or equal to some known series, which is u sub n star, then we would be able to say that the given series is convergent. Okay, so u sub n of our given series is less than or equal to u sub n star of a known convergent series. Then we can determine our series is convergent. Theorem 2 is a method for determining whether a series is divergent. So again, we're looking at a given series of non-negative terms, whoops, wrong pen there, highlighter, of non-negative terms from, again, some term on, okay, is now greater than or equal to that of the corresponding terms of a second series of non-negative terms, which is known to be divergent, then the given series is also going to be divergent. So what this would mean is that u sub n of our given series is greater than or equal to u sub n star of a known divergent series. And so we know some series already. We've learned some in the previous sections. We learned the harmonic series. We learned what we call the p series with p equal to 2. We're going to learn more about the p series today. We know arithmetic series. We know geometric series. Okay, so those are some series that we can use for comparisons. Now, a big warning here. Warning, warning, warning. Okay, do not just compare the first few terms. You have to compare it for the general terms. So we have to compare it for u sub n. We can't just calculate what for n equals 1 it works, for n equals 2 it works, for n equals 10 it works, because we need to make sure that it works for all values of n. Okay, so we need to compare for the general terms of u sub n. So just in summary, shorthand, if the given series is less than a known convergent series, then it converges. If the given series is greater than a known divergent series, then it also diverges. All right, so those are the two theorems. To review some useful theorems for comparison, lesson 20.6. Okay, so we're defining for non-negative terms per the textbook, okay, or the packet that we have. So theorem 1 in 20.6, we already know this one. It's infinite geometric series. So here we have our infinite geometric series, right? Multiply by r every time to get the next term. So what we have is we have that this series is convergent if r is between 0 and 1. All right. Now, it's convergent if r is between 0 and 1, but we know if absolute value of r is less than 1. But remember, in this section, we're talking about terms that have or series that are all positive and no negative terms. Okay. Then we know that it's divergent if r is greater than or equal to 1. Then we have theorem 2, which is the p-series. So we talked about a p-series already. We talked about a p-series where we had, for our u sub n value, if u sub n, the one that we already mentioned in class, was 1 over n squared. N squared we said was convergent. And so this is what we call a p-series, where p is greater than 1. Okay, so it's 1 over n squared, right? So the p is 2 in this case. And then we also mentioned the harmonic. So the harmonic was u sub n is equal to 1 over n. So that one has a special name, and you can call it harmonic, or you can write it out as u sub n equals 1 over n. And that one we learned is divergent. And that is also a p-series with p equal to 1. And there are other p-series where p is less than or equal to 1 that will also be divergent. Okay, and you can look in the text. If you look in the text on page, I think it is page 539, you're going to see a proof for why the harmonic series is divergent. And if we have time, we'll talk about that in class sometime. All right, so that's the p-series. So a p-series is convergent if p is greater than 1, and divergent if p is less than or equal to 1. Okay, and a p-series is just 1 over n to the p. So 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, and so on. All right, so let's take a look at some examples and see how we can put these theorems to use. All right, example number 1. We want to determine the convergence or divergence of this series. Okay, so we're going to go ahead and just start by using the comparison test on this one. You could try the other things out that you know and see if they would work, but we're going to jump right to comparison test since I know that that's going to work, and that's what we are learning today. So what I want to look at here is I want to think about, what do I think is going to happen? Do I think that this series is going to converge, or do I think it's going to diverge? So the first thing I want to think about is, what's my hypothesis? Is my hypothesis going to be convergence or divergence? And to do that, I want to take a look at each of my terms here. So this term or this term, what does it look similar to? Well, and I kind of think that if I were to take away this right here, now 1 minus 0.1 to the nth power is really, really, really small. So that's not going to have a huge effect as n goes to infinity. And if I were to take away what I highlighted in blue there, and I look at what's left, and I have left this numerator is 1, my denominator would be an n. That kind of makes me think like it's very similar to 1 over n, or 1 over n is the harmonic. So maybe that's what I want to try and do, is I want to compare it to the harmonic series, which is u sub n is equal to 1 over n. So this is what I'm thinking, and if I compare it to the harmonic series u sub n equals 1 over n, I know that the harmonic series is divergent, so I'm hypothesizing that it's going to be divergent. So I would always like you guys to write down your hypothesis and the series that you're going to compare it to. Those are your first 2 steps. And then we're going to continue on, and we're going to state what the theorem requires. All right, so what the theorem then states is I need to know about this first comparison, the series to compare to. So what do I know about u sub n equals 1 over n? Well, that's the harmonic. So I'm going to write out exactly what I know about that harmonic. So I'm going to state that the series summation n equals 1 to infinity of 1 over n is a harmonic series and divergent. So in order to use it for comparison, I need to make sure that I know whether it's convergent or divergent and why. So we always state the theorem, or state the series that we're comparing and what we know about that series. Okay, so now we want to compare it. Well, if I'm going to state that it's divergent, if I go back up here, for divergent, What I want is I want u sub n to be greater than or equal to the known divergent u sub n. Okay? So I need my given series to be greater than or equal to 1 over n. So I'm going to write out that statement. And so I say that if 1 over n is greater than or equal to my given series 1 over n times the quantity of 1 minus 0.1 to the nth, then the given series is also going to be divergent. And so I'm writing out what I'm trying to prove. So I'm saying if this is true, then I know that my given series is divergent. Okay? And so now I'm going to prove that. And it's going to seem not that mathy, all right, then compared to what you're used to doing for math. So I'm going to prove this using things that I already know. So some things that I already know are this. And I'm going to write out in sentences. So since what I have here, this side here, this I could pull out the 1 over n from there. And so I can say that this is equal to 1 over n times the quantity of 1 over 1 minus 0.1 to the n. Okay, and I did that because then I have this 1 over n here that's going to be able to match up with this left-hand side of my inequality. And what else do I know? What else I know is that I know that 1 over 1 minus 0.1 to the n is always going to be greater than 1. Right? Because I have 1 divided by a number smaller than 1. So I'm breaking it down into little parts. So if that's always greater than 1, then that means when I multiply that by the 1 over n, then this quantity times the 1 over n has to be greater than just 1 over n. And there I've proven what I wanted to prove, and what I said here I was trying to do. If this was true, then the given series also diverges. So I've just explained why that's true. So my last thing I need to do then is I need to write that out in a sentence. So I write out in a complete sentence, including all of the information that I need. I say the given series is greater than a known divergent series harmonic. Therefore, the given series also diverges by the comparison test. And that's what you want to write out for your final answer here. But really, your final answer is inclusive of all of the work, because the final answer doesn't make sense unless you have all of that support. Do you need all of that support? Yes, you need all of that support. All right, let's take a look at number 2. So number 2 here, sorry, I forgot to erase those little parts. But looking at number 2, let's see what we have. So I have 1/2 times 1/3 plus 2/3 times 1 over 3 squared plus 3/4 times 1 over 3 cubed. So I can kind of see this is broken up into 2 parts. You can see what I have highlighted in green is n over n plus 1. And that's the first term, or first part of that term. And then divided or multiplied by 1 over 3 to the n. All right. Now, I could try and do something like I've done in the past. Like I could try and do that limit test to see if the limit is equal to 0 or not equal to 0. And maybe if the limit does not equal 0, then I'd be able to say that it diverges. So let me just show you. You could try that and see if it works. So I did try that. I checked the limit of u sub n. And the limit of u sub n would be the limit of n over n plus 1 times the limit of 1 over 3 to the n. Let me make this a little bit bigger. And so then that would end up giving me 0. And if that limit of u sub n equals 0, it's inconclusive and I can't tell anything. So now I'm going to look into the comparison test. So if we think about this quantity here, the n over n plus 1. Well, as n gets really large, the plus 1 is insignificant. So really it's kind of like n over n. And n over n would just be 1. So what's highlighted in green here is relatively a 1. So it's 1 times 1 over 3 to the n. So let me maybe compare it to 1 over 3 to the n. And 1 over 3 to the n, I know, is a geometric series with r equal to 1/3. So the absolute value of r is less than 1, which means it would be convergent. So my hypothesis is going to be that this series converges. Okay, and I'm going to compare it to the geometric with r equal to 1/3. So u sub n is equal to 1/3 to the n. All right, so let's state what that means. Okay, so I need to give all my information about the geometric series first. So I'm going to say that that geometric series is convergent. So the series summation n equals 1 to infinity. 1/3 to the n is geometric with r equals 1/3, an absolute value of r less than 1, which is convergent. I always must state my comparison series and whether it converges or diverges. Once I state that, now I'm going to state what I'm trying to prove. Well, if I'm trying to prove convergence, then I need my given series to be less than or equal to the known convergent series, which is this geometric. And so what I have then is I have if n over n plus 1 times the quantity of 1/3 to the n is less than or equal to 1/3 to the n, then the given series also converges. And so now this here is what I'm trying to prove. I'm trying to prove that this in yellow is true. Okay, so we're going to go ahead and do that. And again, it's less mathy than what you're used to and more wordy, more like English. Okay, so we're going to write it out in sentences. So, what can I think about? Well, I can see here that both sides have a 1/3 to the n, right? So let's think about that. What's that quantity of n over n plus 1? So if that quantity of n over n plus 1 is greater than 1, then that would not be what I want. If the quantity of n over n plus 1 is less than 1, then that means when I take a number less than 1 times 1/3 to the n, it's going to be less than just 1/3 to the n. All right, so let's prove that. So let's compare the numerator and the denominator. So since the numerator is n, the denominator is n plus 1, then, oops, too many things at one time. Then I know that n plus 1 is greater than n. So my numerator would be less than my denominator. So n divided by n plus 1 is less than 1. Consequently, when I take a number that is less than 1 and I multiply it by something, it's going to give me a number that was less than the original value. And that's what I wanted to prove. All right, so I did it. So I can write out my final statement. So I say, the given series then is less than a known convergent geometric series with r equal to 1/3. Therefore, the given series also converges by the comparison test. And you can use CT for comparison test. And I just noticed I also forgot in here, and absolute value of r is less than 1. Squeeze that in there. All right, that's example 2. Let's take a look at example number 3. If you think maybe you can do example number 3 on your own, pause the video and see if you want to go ahead and give it a try. All right, so when I look at this one, I'm looking at the 1/2n minus 1. Minus 1 is pretty insignificant as n goes to infinity. Multiplying by 2 here, maybe it's significant, but maybe not. So if I would just start with it's not significant, then I would be left with 1/n. So let's start there. Let's start by comparing it to the harmonic of 1/n. So if I compare it to the harmonic of 1/n, I'm going to hypothesize that it diverges because the harmonic diverges. So I'm going to write out what the harmonic is and what it does. So the series summation n equals 1 to infinity of 1/n is a harmonic series and it's divergent. Okay, so what do I need to prove? I need to show that if 1/2n minus 1 is greater than or equal to 1/n, then the series diverges. Okay, so let's take my denominators. And if I have 1 divided by a denominator, whichever denominator is going to give me a smaller number. So let's compare the denominators and see which one's bigger. So what do I know about the denominators? I know that 2n is greater than n. Okay, then that would mean that 1 over 2n is going to be less than 1 over n. Oh, that's not what I wanted. And even if I subtract 1 from the 1 over 2n, it's not going to give me what I wanted. So that's not helpful, which means it's not going to work. All right, just because it's not going to work, though, doesn't mean we give up. We just try something else. So let's go back to the original where I said maybe the 2 is significant. So let me just erase that. And let's keep the 2 in there. What if we compare it to, instead of comparing it to 1 over n, let's compare it to 1 over 2n instead. All right, so let me just give myself some more space here. So comparing it to 1 over 2n instead. So if I compare it to 1 over 2n, that's still a harmonic multiplied by 1/2. So it's still divergent. So let's write out what that means. It means the series is harmonic multiplied by 1/2, so it diverges. So again, if 1 over 2 to the n minus 1 is greater than or equal to 1 over 2n, then the series will diverge. So again, I want to go ahead and I want to compare these denominators, find out which denominator is bigger. Because if I have 1 divided by a bigger denominator, it's going to be a smaller number. And it might look obvious to you, but you do need to write it out so that it's very clear to the reader. So I can say, since 2n minus 1 is less than 2n, right? That's an obvious statement. Then 1 over 2n minus 1 is greater than 1 over 2n. That's what I wanted. So then I write out my final sentence. Always have a sentence for your final. The given series is greater than the known divergent harmonic series multiplied by 1/2. Therefore, the given series is also divergent by the comparison test. Always state which test you're using. We're going to be learning more and more and more tests. Okay, I challenge you guys to pause the video and try number 4.